my name is Ben, and I've prepared just a handful of notes so we can take a run-up to the following few sessions. And as a bit of a caveat, there's a fairly good chance I've undershot in how sophisticated I've made this presentation. But I think if any direction, that may be a more sensible direction to err in. Okay, so very quickly, I'd just like to go through some of the basics, paint in very broad brushstrokes what we mean by spectral analysis and local spectral analysis, take a glancing look at functional data analysis, and then hopefully there's a part where I start to describe why this might be relevant to the discussion paper we're going to be looking at later on, and then a couple of remarks on some things I'm particularly looking forward to hearing about in the discussion meeting later. Okay, so starting at the very basic level. So Fourier analysis, of course, is about understanding time series, understanding one-dimensional series in terms of a set of contributions from waves at different frequencies. And on this slide here, I've got 4 pairs of waves at increasing frequency as we go up. And the idea is that we can imagine taking one of the smoothest waves, so the flat line from the bottom, and adding some multiple of the wave one frequency higher. And we can do this again, add a frequency higher again, and then add a contribution from the waves at the highest frequency. And now we've got a signal that no longer looks like purely oscillatory, but we have seen how it can be arrived at by taking these linear combinations of waves at different frequencies. And so Fourier analysis really is about going backwards, taking a time series and looking at the frequency components that could have contributed to it, that could have made it up. And so to make this more precise, we're going to talk, I'm going to talk about time series, so real valued time series indexed by tau, and these are these little small case x. And what I'm going to do to try to figure out what the coefficients multiplying the waves at different frequencies is do this discrete Fourier transform thing. So I just take a sum over time of the values of the time series multiplied by some complex exponential. And this is giving me back this capital X, which is indexed by a frequency. And I was going to claim that this is a sort of recipe for recovering the coefficients of the waves at different frequencies. If you're more comfortable with the trigonometric expression for the complex exponential, you can do that. We can translate this to a real part and an imaginary part, and then you can start to see how this thing, which is a complex number, is just a way of encoding the contribution due to one wave and the other wave that was out of phase with it. Okay, but often when we do such a thing, we reverse engineer these coefficients. The values of the coefficients aren't so interesting as the size of the coefficients, so the absolute size. Right, so the absolute size of these coefficients is going to tell us sort of how much is going on in the signal at the different frequencies. It could be positive or negative, but we're just interested in the sort of how much there is, and we call how much is going on at a particular frequency the power or the spectral power at each frequency. And here we can compute that just by looking at the squared modulus of this complex coefficient, capital X. Okay. So, we have gone from a signal. So this is our X, and it could be some displacement of a microphone. It's Davide's sound data somehow. And we can convert these into these complex Fourier coefficients. And then we're not actually interested in the coefficients as much as their sizes. So we look at these spectral powers at different frequencies, which are positive numbers because they're sizes of complex numbers. And then I've taken the log of these powers. For now, it's enough to say that it's just easier working with things that live on the whole real line rather than the positive part. So it's mostly pragmatic, that we look at the logs rather than the raw powers. So that it was in a nutshell the sort of classical Fourier analysis. But now we're going to have a look at a sort of more a local version. Right? So here on the screen we've got a candidate Fourier mode that we can look at how much of our signals sort of is attributable to such a mode, right? But attributable to such a wave over the whole time series. But often we'll be interested in how much of a signal can be attributed to a particular frequency, but only in part of the time, part or a certain window of the whole time interval we're looking at. Right? And we can describe a window, a sort of location, by introducing an envelope or a window function. Right? So here I've got just some decaying exponential, which is sort of describing a sort of mass towards the middle. Right? I can multiply these things together, and I get a windowed or enveloped Fourier mode, right? Which I can move left or I can move right. I can decrease the frequency of oscillation, or I can increase the frequency of oscillation. And then from here, the sort of story plays out very similarly to as it did before. Right? I can try to find these local Fourier coefficients by taking some sum of my time series with the complex exponential, but this time it's multiplied by some windowing function, some enveloping function. And very similarly, I can take the squared modulus of these coefficients to work out a spectral power at a particular frequency, but also localized at a particular point in the time series. Okay. So this is what Davide and his co-authors do. They look at the log spectral powers, right, for particular frequencies and particular times. And it turns out that when they do this, they find that these log powers are very rough. It looks like there's a lot of noise in them, lots of degrees of freedom, a lot of information to try to manage. Right? So they think to themselves it would be much easier, and if there was just some sort of intrinsic smooth process, some sort of lower dimensional process underlying this log spectral data. And that this smooth version is the S, and we're going to pretend that the extra information that's not captured by the smooth, the epsilon, is just noise that we want to see through. Right? So here you may recognize this is a very similar case, it's just a regression problem. Right? There is, so our data now is our log spectral powers, and our signal is our smoothed S, our smooth log spectrum, and then we're pretending there's this noise on top of these epsilons. And yeah, in essence, we can employ sort of regression technology, but constrained regression, constrained in the sense that we want to insist that these S components, the smooth part, really are smooth. So one of the easiest way to do this is to constrain S to lie within a space of smooth functions. And this is sort of what these sums down here are writing. This is one way to ensure that the S's are smooth. You can say that they are formed by this linear combination of smooth functions, right? So where this little b, which is a function of frequency and time, is a smooth function, and this is just a coefficient multiplying it. So if S is just a linear combination of smooth functions, it is smooth itself. It also turns out it's very convenient if these smooth functions can be decomposed, factorized into functions just of omega and just of t. Right. So if you do something like this, then the surface S, right, you can encode it, you can describe it in terms of the coefficients multiplying the known basis coefficients. Right? And so your problem of describing a great big, potentially infinitely dimensional surface reduces down to a statistical problem about getting a vector of coefficients. Right? And we can describe an expectation of the surface via the expectation of the coefficients, and we can describe covariances between function values in terms of covariance of the basis functions, right? Whether we deal with the basis representation of S explicitly or not. So the interesting part of this slide, for me at least, is that later on we're going to be looking at covariance functions that are sort of related to this quantity. And these quantities are notoriously difficult to deal with and to estimate. And partly because this thing looks, if you encode it in your computer, as a four-dimensional array. So as a matrix is a two-dimensional array, this thing would be a four-dimensional array because it has four indices that you can vary and you get different numbers out of it. Not only is it a large, like high-dimensional object, it also needs to satisfy certain sort of positive semi-definite properties, which in practice are quite hard to check, quite hard to enforce unless we're sort of clever about it. So back to this storyboard again, we started out with our real signal, went to complex local Fourier coefficients, from which were complex numbers. Then we went to the local powers, which were real positive numbers. We took the logs of those things back to the real line. We could look at a basis representation of the smooth log spectra, right? So back to real numbers, vectors of real numbers. And then now we've ended up with these covariance functions, which are pretty weird things. So four-dimensional arrays, and they have to satisfy these positive semi-definite conditions. So that's the sort of sequence from raw data to the sort of objects we'll be looking at soon and this evening. And now we start to move into David's realm. I know. Well, how is he going to use this technology? Well, he and his co-authors introduced the idea that they're going to record sounds, words from different people saying different words in different languages. From each of these sound files, I can compute the local Fourier power, and I clean it to get these smooth log spectra. And they have indices for words, for speakers, and for languages. So these are data objects. And now we can imagine that Davide has got assembled a room full of, say, 10 French speakers and asked them all to say the same word. Okay. So from each of them, he's going to get a capital S, a log spectra for that word. Now, all these people, hopefully, are going to sound sort of similar. Right? There's going to be some sort of common element to the way these people are pronouncing the words. Right? And this I've described as the mu. So for a particular language, saying a particular word, right, the sort of common element amongst all the speakers is this mu. Right? And the difference from the common element in log spectrum is this R, these residuals. So this R represents the difference from the average speaker saying the same word in a particular language. Right? And then, David, you can look at the differences, right, of each of these 10 people in the room from the group mean. And you can start to characterize the differences between the mean and the individual people. He's going to characterize that in terms of a covariance specification for the R's. And one of the interesting things these authors do is they assume that this covariance structure, right, between the speakers of the same word actually applies to all the different words within the same language. Right, so now we have one covariance function, right? So this big high-dimensional object, but there's one for each language, and they're going to use this to characterize a particular language. So there are obviously many things that I skipped over, both to do with Fourier analysis and functional data analysis, and my very brief and crude description of the work we're going to hear more about. So one of the interesting things that I skipped over was just how you go from these log powers to the smooth spectra. And I sort of brushed it aside, just said it was a constrained regression problem. Turns out it's slightly more complicated than that. So the noise in this problem is such that we require a sort of more robust approach. So a bit like linear regression, constraint regression, but with some extra techniques to try to sort of robustify the process. And there's also the issue that these sound files, before they can be used to estimate the S's, need to be aligned in time, right? Which is a sort of separate issue, an interesting issue, but not one I think we've got time to go into today. Right? There's the main issue, the one I'm particularly interested about, is how these authors are going to try to estimate, right, these covariance structures, which are characterized in languages, from presumably not a huge amount of data. Such a task is stuff to give a statistician nightmares, right? Because these are very high-dimensional objects, and in general, estimating them is extremely difficult without imposing some quite strong structural assumptions. We'll see just how that happens later on. So, yeah. It'll be interesting to keep an ear out later on in the proper meeting to hear how the authors, how reasonable, or if they can convince you that this assumption of a common variance over words within a language is a good assumption to make. I'll be interested in seeing that, and they have some material in their paper to describe why that might be a sensible thing to do. Right, of course, we want to know how the variances characterized in language will be estimated, and then crucially, we want to know why we've done this in the first place. Right? What are the authors going to be able to do with these covariance structures once they've estimated them? I'm not going to give away that surprise. Okay, so if you go to your library, you will find shelves worth of material on this stuff. But I just thought I would highlight two of the sources that I would regard as particularly important and particularly famous. The Brockwell and Davies book for time series, but has a lot on spectral analysis. And of course, a book by Ramsey and Silverman on functional data analysis. So that's statistics for describing objects like the capital S, the log spectral power.
My name is Davide Pigoli, and I'm going to give an overview of the paper we're going to discuss more in deep later in the afternoon. So I will start with a bit of a context. So what I think put our paper in a slightly different position with respect to all the existing work on sound analysis and data analysis is that we are trying to consider populational sounds, as Ben described in the end of his presentation. So the idea is that we are trying to use statistical methods where the sound is what will be the statistical unit. So this is a pretty different point of view with respect to, for example, speech recognition, where you are looking at a single individual time series, which is your sound. So we have multiple time series or multiple functional data, as we have seen. So why we are interested in looking at this context? Well, first of all, because the final goal is to use these techniques in historical linguistics. So this is a branch of linguistics that studies how languages develop and change in time, or possibly also in space from one region to another. And the idea is they want to look how languages are similar or different, and how they move from one to another. And this is interesting from a purely academic point of view, if you want, because of languages is an interesting subject. But there are also some relevant application in related areas such as anthropology or genetics. So information that comes from population, relationship between populations is important in genetics, for example, or of course sociology if we are talking about modern day languages, or even some economic models which somehow take into account language differences as a cost in trading, for example. So this is very generally the context we are moving in. And specifically our collaborators, our linguistics collaborators, have a goal, which is the final goal of their life, is to reconstruct how the ancient languages sound like. So we'll be able to reproduce how, for example, a Latin speaker would speak or how a Greek speaker would speak. And so they are working on this. They have been working on this for a while now. As you can imagine, it's not an easy topic to address. And so what we are doing at the moment is trying to use some intermediate step in the evolution of a language that they can, for which they can use some proxy. So, for example, they go in remote Greek villages and recorded how people speak there, and they say, okay, this is a good proxy for, I won't say for ancient Greek, but for some intermediate step in the development from ancient Greek to modern Greek. So they have modern Greek, they have this intermediate step, and so we want to extrapolate back to ancient Greek. So this will be their final goal. We are not there yet, so this is not what today's discussion will be about, because today we are talking about the first thing we did in our project, which is try to model this language change, and to learn how to model that, we started from existing languages. So, in particular, we worked on Romance languages. And so we focused on this pilot data set, which include 5 Romance languages, well, actually 4 Romance languages, of which one of which contains 2 varieties, which is Spanish, because we have Spanish from people from Spain and Spanish from people from Mexico. And so we are going to use this data set to learn how to explore language change. So up to now, what people are doing to explore similarity between languages is looking at textual or phonetic transcriptions of a word. So not only how the word is written, but also how it is pronounced. However, these phonetic transcriptions are normative expression of how the word should be pronounced as written by in the dictionary. So sometimes we have little to do, or well, it's not true, they have some to do, but they ignore the variability that is present in the language. And while we want to take into account the variability with which people speak in practice. And to do that, we actually start from recorded sounds. Okay, so Ben already talked a bit about this, but I just want to give a one-line explanation for why we cannot simply work with sounds as they were vectors, because the point is that if you start from 2 sounds and you treat them as vectors and you take the average of the 2, what you get is a sound which is which contains both of the original sounds at half of the volume. So it is not something that is linguistically in between the 2 sounds. So now let's see if the technology supports us, and we'll try to play it. Okay, so I will play first a version of a French speaker which says the word for 1. Okay, so you see I repeated that, the word on, or something like that. I don't speak French. And this is a Portuguese for 1. Okay, now if I play the average of the 2 sounds. So you see, it's not something. It's kind of a mix it's a kind of a superposition of the 2 sounds, but is not something really in between the two words as we can think of them. Okay, so this is the reason why we need to move to a frequency representation, a Fourier representation of the sounds to be able to explore the changes. So as Ben explained before, we start from the sounds, we apply the local Fourier transform and the logarithm, and we get this object on the... Does this work? Yes. So we have this object, which is the local Fourier, the logarithm of the power of the amplitude of the local Fourier transform, starting from this sound, and then we apply the smoothing and the time warping that Ben mentioned before, so that the sounds are comparable across each other, and we get this is as our object of interest. Now, in the discussion later, we are going to go through these steps more in detail and discuss all the technicalities about that, but I don't want to go into that here. Just let's keep to the broader picture. So we get a population of these sounds for each of the language that we explore. Okay. Now, so just to give an overview of the data set, we have 23 speakers divided in the 5 languages, and almost each of them pronounce 10 different words that are the words for the number from 1 to 10. Now, on one hand, this is a very restrictive and specific dictionary, of course, but on the other hand, from a linguistic point of view, these words are not a particular set, so they are quite a good representative of the dictionary, although it's still a very restrictive subset of the dictionary. And so from now on, I'm saying that something is true for a language, you can keep the small note, which is when I say language, I mean the subset of the word from 1 to 10 for that language. Okay? So now, one of our working hypotheses is that what is a property, while the mean of these log spectrograms is expected to change from one word to another, the covariance structure, the error around, the variation around this mean, is a property of the language and is not specific of a word. Now, this is, of course, a working hypothesis, which tries to explain a phenomena, which is, for example, if you enter in a room full of, with 2 different tables of people who speak 2 different languages that you don't know, you can still kind of hear that the 2 languages sound different. So what is that? What is this element that you recognize in a language that you can say, oh yeah, this sounds like, or maybe this sounds like this language, even if you don't understand the specific words. Now, our working hypothesis is that this feature of a language is the variability around the mean. So this is a kind of a mathematical representation of these words I just said, so that we model our log spectrograms as a mean which depends on the word that is being pronounced, plus some process, some stochastic process, which has 0 mean, of course, and whose covariance structure change with language, but not with words or speakers. Now, of course, when we say that, we mean that what we really mean is that the variation between language is much larger than the variation within language or within speakers. So we can treat this as the main effect in a sense. Okay? Okay, so if we do that, we can simply reorganize a bit our data, and we can remove the mean from each word and treat the residual we get as a repetition from this, as replicates from this process, and we can use these residuals to estimate the covariance structure at the language level. So this already a selfish reason to do this is that we suddenly get a much bigger data set to estimate the covariance, which, as Ben mentioned before, is a challenging problem. So a good thing that we can, an advantage of using this approach is that we can get a bigger sample size. Oops, sorry. Okay, so a second assumption that we are taking, which I'm not going actually to explore in too much detail, not now and probably not even in the discussion later, is that this object is still too high-dimensional. Both, in a sense, computationally as well, but mainly from a statistical point of view, it's too high-dimensional to estimate in an accurate way with the sample size that we have. So a common thing to do, we do in high-dimensional statistics, we put some structural assumption. So there are many of them. You can use sparsity, you can use reduced rank. What we did, because it sounds reasonable for the kind of problem that we are dealing with, is that we treat the covariance as separable, so that the full 4-dimensional covariance is the product of a covariance in time times the covariance in frequency. So essentially what we are saying is that the covariance between frequency does not change across the world, and the covariance in time does not change across the frequency. If we do that, this is a second trick that suddenly increases, in a sense, our sample size, because that means that all the points in the other direction can be averaged across to get more statistical efficiency. So what we are doing is marginalizing in one direction, so using the marginal covariance function as estimate of the covariance between time and the covariance between frequency. Now, of course, this factorization is always defined up to a factor, because you can always put a multiplicative factor in front of one covariance and divide it on the other side. So here you have a liberty on how to treat this, and what we did is to choose this normalization, to choose this normalization in both time and frequency that guarantees that the product of the two get the correct total trace for the 4-dimensional operator. So again, this is a working, I called it a separable approximation, because we don't really believe this is really true, but we think that what we are missing is not that relevant from a linguistic point of view, and that, again, is an approximation we need to do in practice to make things work. Okay, so for example, once we have done all of this, we get this covariance function between frequencies for the 5 languages. So as you can see, they appear to be different. So this supports our working hypothesis that this object contains the differences between the languages. The time covariance frequency, the time covariances, I don't show them. They also show some differences, but are less pronounced than the frequency one. Okay, so the question is, of course, since we are statistician, is this a real different, or is just a fluke? Is just the variation? Is just coherent with the variation in the covariances? So we developed some strategy to test the fact that these frequencies are different, or the same or different. So I need to take a bit of a step back here. So let's go back to a simpler scenario first. So let's say that we want to test the sample, so the quality of the covariances between two samples of functional data, of univariate functional data. Now there are many different approaches that you can use to carry out this test. A lot of work you can find in the literature, but I'm going to present one because it's particularly easy to generalize to our setting, to our scenario. So that's why I'm going to present this one. So, and what I'm going to present is a permutation test. So if this, under the null hypothesis, if this two samples of functional data are generated from the same mean, and have the same mean and the same covariances, means that the curves between the two samples are exchangeable. So I can use a permutation strategy where I permute the label between the two samples, I recompute my test statistics, and I use this, and I do that many times, and I use this to build a permutational distribution for my test statistics. So that means that all I need to apply these procedures is a test statistics that capture the fact that the covariance are different. So for now, let's call that a distance between d between the two sample covariance operators or covariance functions. So if I have these ingredients, I went a bit ahead of myself. So this is the description of a procedure of a permutation test. So again, we permute the labels, we recompute the test statistics for each permutation of the labels, and we can compute the p-value by looking at the proportion of these permuted test statistics that are larger than the one that of the original sample. Now, this is correct if the two groups have both same mean and same variances. If the group have different mean, we need to apply this to centered observations. Anyway, this works only asymptotically in any case, so it's not a big problem, but centering the curves here. And then in our case, we are going to work on the residuals that have already been centered. Okay, so now the question is how to define the distance d between the two covariance operators, and again, you have a lot of choices here. But one choice that we show that works a bit better is a one that takes into account the geometry of the space that you are working with. So if under the usual assumption for functional data, so that essentially they are square integrable function, you get that the covariance operator is a self-adjoint trace class with non-negative eigenvalues, of course. And so you have this essentially you have these constraints on the eigenvalues that make the space non-linear. And that means that you can embed that in the space of symmetric operator, which will be the equivalent of space of symmetric matrices, and treat everything as linear. But you are not taking into account the properties of your object, and this leads to a lower power, essentially, a lower power. So so essentially there are two large families of distances that you can pick from. One that ignore the nonlinearity, and this could be the Hilbert-Schmidt distance, which is the same as Frobenius distance for covariance matrices. The spectral distance, which simply look at the largest eigenvalues of the difference between the two operators, again, something that ignore the structure that is there. Or you can look to a second family of distances, which are the one that takes into account the geometry of a space. And this is, for example, the square root distance, which what does is using the square root transformation to map the covariance operator in the space of symmetric operators, and then there you can use your linear metric, and and this is one way to take into account the nonlinear geometry of a space, or a bit more complicated, the procrustes distance, which has been which we extended to the case of infinite dimensional operators, and this account for essentially the way I understand that is that the procrustes distance account for the fact that the square root is not unique. So any transformation L here essentially get you back to the original. Any transformation L in the space of symmetric operators gets you back to the original covariance. So you have this arbitrarity, and you want to get rid of that by minimizing over all the unitary transformation, of the transformation U, over all the unitary transformation U in the transformed space. So it's a bit of a technicalities here, but the idea is that, again, is a metric that takes into account the geometry of the space, and previous work I've shown that this essentially gives us a better power in the test than the previous metrics. Okay. So now how we generalize this to our setting? We need to treat multiple sample of functional data. So we want to use the same strategy. We just need to define a test statistics that works in this case. So instead of looking at the distance between two covariance operators, we are looking at the variability with respect to, in some sense, a barycenter of many covariance operators. So how we define this barycenter? Again, using the geometry of a space, using the sample threshold mean. So we minimize the squares distance between, we look for the covariance operator object that minimize the square distances between the one we have observed. And so again, this depends on the distance we choose. Let's just focus on the square root distance here, for example. What you get is simply you use the square root transformation to map everything in a linear space. You use the traditional average there, and then you use the square transformation to go back to the space of covariance operators. And this gives you a center point for your, let's say, 5 covariance operators that are the 5 different languages. Okay. And so once you have this, you can repeat the permutation test procedure exactly in the same way, using as test statistics the variation with respect to the center point. Because, of course, you expect that to be larger if the covariances are different, and to be smaller if the covariances are the same. Okay, so we applied this to the sample covariance that we have estimated for our both frequency and times. So first, we, as a check, we test separately for each word, and you see the p-values are pretty large, so there is no evidence that there is a change in covariances across the different words within each language. But then if we check the differences between languages, you see we have a strong evidence for a difference between language. Now, one objection here could be that it's just a fact that we have a larger power here, and it may be. However, that also means that with this sample size, which is the like usual available in this kind of linguistic study, there is little point in trying to model even if there are differences across words, there is little point in trying to model them because there is too much noise there. While it's important to model the differences between languages. Okay, so that was the results for, this was the results for the frequency. Now this is the result for the time. Same story, I'm not spending any more time here. Okay, so finally we get to the more interesting part, so how we want to use this. So we I described the data sets, I described how we process that, I described what modeling assumption we are doing and how we check that. But what actually we want to do with that? So what we want to do is modeling the language change, and now this is possible using the decomposition that we have built in. Because if we see that one word from one language comes as generated from the mean for the word plus the covariance structure of the language applied to the speaker-specific residuals, we can use this decomposition to model how the same speaker can be projected into a different language. So essentially, we move the speaker-specific residuals from French to Portuguese, and we reconstruct back what the sounds of that speaker will sound like using the sound generating characteristics of Portuguese language. So in this way, we can project one speaker from one language to another, and we can also reconstruct a smooth change interpolating from beginning to end all these different components of the process, except the residuals, which stays constant. Okay, so for the mean, this is easy. You can just use a linear interpolation. For the covariance, again, you have a problem of the nonlinear geometry of the space, and we can use. You can use a geodesic path, which hopefully is consistent with the choice you have made for the distance before. So in our case, we used the Procrustes distance for the test, and so we use also the Procrustes geodesic for the interpolation, which is also a lot of interesting mathematical properties, which I'm not going into detail here. But it's not the only possibility, but it's a useful one to consider. So, for example, this is what would look like the smooth path for the mean and covariances moving from French un to Italian uno. So this will be a mean, the time covariance. You can see not that large changes in the time covariance, but a more apparent change in the frequency covariance. Okay, so this is the idea of how we want to use this data, and so I will try to also play. We can also reconstruct the sounds, so I can try to play it. So it didn't sound too well before, so I'm not sure you will be able to hear, but let's try. So let's see, for example, the move from the French for 7 to the Portuguese for 7. Sit, 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 sit. Okay, so it started back again. So it starts from set and go to such. Okay. And now the nice thing here, I didn't use a true Portuguese speaker as endpoint. So this is the projection of the same speaker from one language to another. I can instead use one. As an alternative, I can use a true Portuguese speaker as endpoint. For example, looking to the one which is closer in residuals to the French speaker. And this will be what it sounds like. Okay, you see a similar dynamic. The quality of the sound is slightly better, although I'm not sure you can hear from here, but the quality of the sound is slightly better because of the problem I'm going to talk in a moment, which is the phase component. Okay. So just to wrap up, a few points for discussion. So this one are the one I I discuss with myself, but then of course hopefully other people will bring other perspective. So I hope what we are trying to do is to use functional data analysis techniques to bring to analyze acoustic data from a population of speakers in linguistics, of course. So we use this pilot data set to check our working hypothesis and to learn how to explore sound changes. Now, of course, how much of what we saw depends on this specific set of words and languages, of course, because to be honest, we also consider a family of languages which are not that disparate from one another. So how these assumptions work when we go to larger dictionaries, larger families, or broader set of languages, etc. Possible other applications of this kind of ideas. One we would like to see if it works is voice translation. So of course, which will be a bit of the opposite of what usually people do, but in this case, how to translate your words in another language, but keeping your voice characteristics. So for example, if there is an actor which plays a character, maybe in a video game, and we want to translate that video game in another languages, but we want the actors to be still recognizable in the second language. Now, of course, to do this, first thing you need to work out is having larger dictionaries, of course, and possibly also how to extrapolate towards words that you have not observed, something that we discussed before. But more closer developments from a statistical point of view, we still need to learn a bit about the properties of this path, of this changing path. So what is the accuracy of this and what's happening in between from a statistical point of view. From a practical point of view, so we run all the analysis on the amplitude of the Fourier transform because it contains all the linguistics information. However, when you reconstruct the sounds, you also need a phase component to back transform the Fourier, to build the inverse Fourier transform. And how you do that? So in practice, I used the phase from one of the speakers, because it's true that the phase do not contain any linguistic information, but still it cannot be anything. It needs to be the phase of a sound. Otherwise, you cannot reconstruct something that sounds like a sound, like a word. What to do with that? So if it's possible to extend this analysis to a phase, still an open question, because of course the phase is an even more complicated object to work with. It's an angle everywhere, etc. And I already mentioned generalization to broader dictionary and languages, etc. So these are some of the discussion that we are having between us at the moment, and maybe we can kick off some more discussion later after the proper discussion meeting. Thank you.